Hello, this is my first video in a while. I wanted to showcase a small piece of a project I've been working on earlier this year. The larger project, the idea was I'd build something in C totally from scratch, so I'd only be able to use the standard C libraries and the Unix system calls, and everything else I would build myself. While the larger project is still unfinished, I wanted to demo a testing framework I wrote to help aid with the project development. So the idea here was, as my project got bigger, testing became more unorganized, and I decided I needed a modular way of testing my code consistently, and I thought it'd be fun to also build this from scratch to kind of continue the theme of the project. So anyway, the first part of this video, I'm going to kind of do a little demo, show you how to use it. And then the second part of the video is I'll go into the actual implementation of the framework and show you actually how it was made. So, all right, let's get started. If we go into my terminal here, this is the directory that holds all of my code for the large project. And we can see it's organized a certain way. So there's all these different modules and they end in source, for source code. And if we go into certain directories, we can see that they have an even more specific structure. So this is a util module, which I wrote for miscellaneous utility code. In here, we have different implementations and header files. And then we also have this test subdirectory. If we go into GC, which is for garbage collection, it's the same thing, right? We have all this code, and then we also have a test subdirectory. So, as you may have guessed, the way this is organized is we are going to have a directory which holds a modular piece of code, and then in that directory, we're gonna have a subdirectory called test, okay? So for this video, I made a vlog directory for code for this vlog, and inside I have provided two files, a calculator implementation file, calc.c, and a calculator header file. In these files, we are going to implement a very simple calculator, which we are then going to test. So I've written some boilerplate code already, and then we're gonna add to it just to practice testing. So the boilerplate code I added, if we go into calc.h, I've made this VC add, which all it does is adds two numbers. And if we go into the implementation file, we can see it does just that, right? This is pretty simple. You might be like, why do we need a test for it? But it's just for the demo. So now, if we actually go into the test subdirectory, we can see how to further organize testing code the way my framework expects to see it. So if we go into the testing subdirectory, we can see we have identically named calc.h and calc.c and calc.h files. Then we also have a mod.c and mod.h. I'll mention what that is at the end. If we go into calc.h in the testing subdirectory, we export this testing suite called calc suite, which is going to be the test suite which tests our calculator. Okay, now the question is, how do we add tests? How do we define what this suite is? For that, we go into the calc.c, the implementation of the testing file, right? So again, in here, I've written some boilerplate code. The first thing I defined, well, technically it's the last, but the most important thing I defined here is the calc suite, which is what we exported in the header file. The suite comes with a name, which we will call calculator suite, and it comes with an array of tests. The first test I made is called VC add, which is going to test the function we were just looking at. The name of it is going to be calculator add. We give it a timeout in seconds, 5, and then we also give it the function that is going to be run. To add VC add to our suite, we simply add a reference to it, and we make sure that our test length is equal to the length of elements inside the test array. So anyway, if we were to run this right now, which we can do, all we would do, we have to run make. The way this project is set up is that it makes an executable binary, which actually runs the program you wrote, and then it also makes a test binary, which will run the tests you wrote. So if we want to run this test, we do /test, which is the name of the testing binary, and it'll run all of our tests. So we can see that this project already has a few modules. It has the utility module and then the garbage collection module, which has all of these tests. And then there's the vlog module, which only has one test, the test we just made, and it is in the calculator suite. So it succeeded, great. Anyway, let's fill this test out now so that it tests the add function we wrote from earlier. We are going to use some functions from the actual testing source module. You may have noticed from earlier that I have included this header file, assert.h. This basically provides a bunch of functions that you can use in your test to confirm things are running as expected. To run these functions, you need to provide the chunit test context. So basically, when the framework runs all of our tests, it's going to run them one after the other, and for each one, it's going to make a new testing context. You use that context to run functions that are defined in the testing module. You don't need to really know what's inside the context, but you need it to run assertions and other functionalities. So let's see this in action. So we're testing addition, right? So let's maybe set up an addition problem. So we could have int64t x equals 10, y equals 15, right? And our result, I'll say result equals x plus y. So this would be our, actually I'll call this expected result. And then we'll have int64t and this is going to be vc add x more y. So we would hope that both expected result and actual result are the same thing. They should both be 15, but how do we know this for sure? When the test runs, that's where the assertions come into play. So what we're going to type is assert, and then we get a selection of assertions we can use. We are going to use assert equal integer. We provided the test context, then we provided the expected, which is going to be expected result, and then we also provided the actual result. And this would be one satisfactory test for our addition function. And we would expect this to succeed. So if we go back to our terminal, we rebuild, we run test, everything works out. Our test still succeeds, looking good. Of course, you probably are interested in what happens when it doesn't succeed. So we could go back to our calculator implementation here. And let's say we screw it up. Let's say we actually return x plus y plus 1. Now what happens? Well, we have to rebuild our testing binary. We run it, and we could see we have an actual of 26 when we expected 25, and this is in the calculator add test in the calculator suite. So this is as much information it gives us. This looks similar. Regardless of what type of assertion you use, it should print out the expected and the actual. Assertions are probably the most obvious thing my framework checks for, but it also checks for 3 other things. The second most obvious would be, what if our program crashes when running our user implemented code? Like for example, let's say I have 2 other integers and I divide them. So in this case, we'd expect the program to crash because we're dividing by 0. Anyway, let's see what happens to our testing framework when we run it. Let's clear this. That's nice test. We can see now we no longer get a warning, but we actually get a failure. So maybe later I'll learn to add more information to this message, but for now we know for a fact that our test actually crashed. This is more fatal than simply an assertion warning. The third thing we check for is also somewhat obvious, and you might have realized from when we were making the test, which is that you provide a timeout. So let's say this timeout was 1 second. But we decide for some reason in our add function, we're just going to run forever. Can the framework handle this? Well, let's see. And it can. We get a timeout. The process ran for over 1 second. And that's a warning, right? As a proof of concept, if we made this 4 seconds, we would expect our test to run for a little bit longer. And there we go. That was probably about 4 seconds, right? We get the same timeout warning. The function did not succeed. Anyway, the final thing my framework tests against, which is somewhat unique to C, is user-caused memory leaks. So in C, you tell the computer when you want dynamically allocated memory, and then you also need to tell the computer when you're done with the memory you have allocated. This is different than things like Java or Python, where the memory is managed for you, and you don't need to tell the computer when you are done with a piece of memory. Instead, the memory management system will determine that for you. Anyway, so we could see an example here. So for example, let's say for some reason in our add function, we wanted a piece of data for some reason, and we called malloc. This would be an obvious memory leak, right? Because we call malloc, we don't really return a reference to the data. It only lives in this function, but the dynamic memory we allocated is never freed. So it'll just persist for as long as the program lives and never really be used or recycled. Now, the issue with this is that if we go back to my testing code, or my running the testing code, we run make, run the test again, we see everything succeeds, even though there's a clear problem with the code. So how can we tell the framework that we're using memory and we want to make sure we want to check for memory leaks? The really easy way to do this is that the framework provides wrappers around malloc and free that simply just keep count of the number of times you've called malloc and the number of times you called free. And if they don't match up, there is an obvious memory leak. Obviously, I would understand that more complex types of memory leaks are probably possible. This is like a very simple check, but for our purposes, I think it's actually pretty helpful. So for example, if we change this to safe malloc, and then we just provided one more parameter, which isn't really important for this video, but just gives the framework a little bit more information. Now, if we run, we can see we actually get a warning. We get a memory leak in the calculator add function. And we can go back and we can say, oh, obviously we called safe malloc, but we never called safe free. Again, given that we use safe malloc, we have to use the safe free wrapper to free the data. And if we run this again, everything works out again. So great. Last thing I wanted to do is show my testing framework in action. Obviously, this demo test we made is kind of small and not really that practical, but I do use the testing framework all over my project for more practical purposes. For example, I do have a data module which defines simple data structures like linked list, array list, this thing called a broken collection, which is kind of a mix between a queue and a stack. And if we go into the testing subdirectory, we can see we have our data.c, and we can see all the tests I've made for it. So here's some linked lists tests, as well as the linked list module. Here are some array list tests, as well as the array list module, kind of short. Here's the broken collection tests, which are a little bit more complex. And at the bottom, we should have the broken collection module. Let's see, where would that be? Or broken collection suite, I should say. And we can see we have all these tests just for this one data structure. So anyway, now we can move on to the actual mechanisms of the framework and how it works under the hood. So in order to understand how the testing framework runs, we are going to be investigating this testing source directory. It contains most of the source code that the testing framework relies on. Most notably, the chunit.c file basically contains the core of the testing framework. And what we will be investigating most in detail will be this function, the chunit run test. Basically, the entire rest of the testing framework, like testing suites and testing modules and printing out the tests, basically relies on this function to run one singular unit test. To understand how it works, we really just need to see the first few lines here. Most notably, we have a call to safe fork, which is a wrapper I wrote for just the normal Unix fork call. If you're unfamiliar with fork, it is an extremely useful call which will take the memory space of your process, which is running, and it will copy it into the memory space of a new process. So basically, it clones your process. The process which does the cloning, which in this case is going to be the framework process, is known as the parent process. And then the new process that spawns, that's the child process, right? So in this case, the framework process is going to persist throughout the entire running of the program, whereas child processes will spawn individually to run individual unit tests, and they will die, and then new ones will be spawned for new tests. So you might be asking why this is the case and why we can't use just one process, why we need to spawn new programs. While it might be possible to do it just in one process memory space using signal handlers, which I was not that versed in, so I decided to use fork instead. I found this approach a little bit more convenient. The idea here is that when individual unit tests run, they might crash. If we think back to when our add function divided by 0, that crashed the entire test process, right? And if we were using just one process, when that individual unit test failed, the entire testing program would end. So maybe we're running 100 tests and the 5th one fails, and now the 95 other tests don't even get to run because our program has exited, right? And that isn't a huge deal, but it would be annoying if you could only debug one test at a time and you could only see one failing test at a time. So I decided to use this fork design, which if a child process running a unit test failed, the parent process, the framework process, could just retrieve that information and then move on to the next test. So even if 10 of your tests catastrophically, fatally fail, the framework process will persist and be able to report all of the failures at the end regardless. Now this came with some tricks. So we can see that up here we have this called a pipe. Which is kind of intuitively named, will basically set up communication between a parent process and the child process so that they will be able to talk to each other and monitor each other's status. While this can be used probably for more, while this can be probably better used in my framework, it's only used for the child process, the unit test. communicating failed assertions back to the parent process. So what we're going to do now is we can see here, in this case, well, one side note is that when you run fork, the way you can determine if you are now in the parent process or the child process is that the parent process, the value returned will be the ID, the process ID of the child process, whereas in the child process, the returned value will be 0. So what that means is that when this code runs, if we make it to the inside of this if statement, when PID equals 0, we know that we are in the child process. Whereas if PID does not equal 0 and we continue, we would know that we are in the parent process. So right now we're going to investigate the child process function call to understand how this works on the unit testing end. And then afterwards, we can look into the parent process function call to see how the framework process monitors a unit test as it runs in a separate process. So the child process code resides in this assert implementation file. And it's pretty simple. All it does is it runs the test for the most part, and it checks for memory leaks at the end. So if everything works out, we tell the parent process that there has been a success and there are no problems. We can see just a few lines above, if there's a memory leak, we actually tell the process that there's been a memory leak. And in that case, the parent process knows to report a warning instead of telling the user that the test succeeded. This is gonna hint at how our assertion calls are coded. So for example, here is assert true, very simple. If the given value is true, we just do nothing. However, if it's not true, we're going to tell the parent process that there's been assert true failure. We shoot that through the pipe, and then we just exit. No need to run the rest of the test. There's already been one warning, something's gone wrong, we can just exit. And basically all of the tests, all the assertion calls are written in this way. We can see sometimes we need to write a little bit more data. For example, when we had the assertion error with add and 25 didn't equal 26, the parent process needs to know what the expected and the actual values were to print that out to the user. So we actually send that through the pipe. And the parent process foreseeably gets this data, and then the child process can exit. One thing that wasn't mentioned earlier that is interesting to note is that all the assertion calls have this test lock, which means that if you call two assertion calls in parallel and they both fail, only one will be reported to the parent process. This is nice because this means that you can call assertion calls in parallel and nothing will break. The testing framework will not break. So you can make a test that spawns many threads and is calling all sorts of assertions in parallel for some reason, and it would actually still work as expected, which is something I do in some of my project code modules where I want to test that thread-safe data structures are actually, in fact, thread-safe. This is how I do it. I spawn many threads, and then I do all sorts of operations in parallel, and then I assert that things are working correctly. Anyway, the last function we'll look through for this video is this function right here, the chunit parent process. This function will run in the parent process while a unit test is running in the child process, and it will monitor the status of the child process. This function is a little bit longer and a little bit more involved than the child process function. So I'll just go over some quick main points here of how it works. The first thing we really do is we wait for the child process to exit, or we wait for the timeout to be reached. If the timeout is reached, we simply kill the child process and then we return from the function. Next thing we do, if we make it past that part, we know that the child process has concluded its running, and we can extract information about how it exited and or information it sent over the pipe. So the first thing we do is we check the exit status. If it did not exit normally, we report that as a fatal error. If it did exit normally, but it used special codes, for example, the framework has special codes for when certain things go wrong, maybe the pipe, there was an error setting up the pipe or a mutex, then this is reported, and the user will see this as a framework error, not an error in their test. And that means either I did something wrong writing the framework, or maybe they should just run it again. Something out of our control is awry for some reason. After this part, we check if the user exited with a status code bigger than 0. And this would also be reported as a fatal error unless the test is marked as should fail, and that would be reported as a success then. Lastly, if we make it past all those points, we know that the child process exited successfully, there's no fatal error or anything, and now we can read from the pipe to make sure that there wasn't an assertion warning or a memory leak for that matter. This is done by reading one singular code or one singular tag. It's this CH unit test result from the pipe. It's guaranteed that if the unit test does conclude successfully, that it will send at least one of these tags. After reading the tag, then we go into this big switch statement, which determines how to handle it. For example, if there's a memory leak or any of these easy assertions, we simply log that in the result and we return. If there is an equality assertion warning, then we will actually read the values from the pipe afterwards. So, for example, earlier when we were testing the addition function and 25 didn't equal 26, that was sent over the pipe. The way it works is the parent process reads this tag that there has been an equality error, an assertion error, and it knows that following this tag are going to be 2 more integers. That's what's done here. After reading the values, we just return. The only special case here is maybe with strings, because now we aren't really working with fixed size integral values, but we're working with kind of a variable size string, right? A string could be very long potentially. So we need to understand how much we need to read from the pipe. So the user program sends back the sizes of the strings after the tag, and then the parent process understands that with these sizes, we can then read the expected and actual values from the pipe and allocate the correct amount of space for these values. And that's basically it. Everything else kind of stems from these 2 functions, the parent process, the child process, the run test function. So that kind of concludes the mechanisms of the framework and also what I'll be talking about in this video. So thanks for watching, and I hope to post more videos soon.